Welcome to lecture number 18. So, what are we going to do today? Let's see. So, let's look at this. So, what we have done is that let's look at, we have learnt about band diagrams. We were learning about energy and K band diagrams. That's what we did. Then after that, corresponding to EK diagram, we examined that we could have E position diagram, and that we did in lecture number 12. If you recall, what we had done was that we had drawn a band diagram, EK diagram, saying that if this is K axis and this is energy axis, then for some direct semiconductor the conduction band looks like this and a valence band looks like this. So, we could plot another diagram where we could have something like this as another semiconductor, where we would say that this axis continues to be the energy axis, but axis is a position axis, and this was the EC and this was EV, which gave us the, and this was the band gap. This was the EG, which is the band gap in this material, and this is what we had done in lecture number 12. And then from this point on, once we started with this, we started deriving then the carrier statistics, equilibrium carrier statistics, and we went up to carrier freeze out in the previous lecture. Now we are moving on. What we are going to do in this lecture is we are going to learn about junction band diagrams. What happens if you join two semiconductors together, and then how would the band diagram of this kind, E versus R type of band diagram look like in that case if you join two materials. Example would be, well, to best of my knowledge, semiconductors by themselves are not really interesting, meaning thereby if I give you silicon, what do you do with it? I mean, by silicon alone as such probably has not much utility. So, what is necessary, yet you know that silicon is workhorse of our electronics, microelectronics. So, how does that happen? You also know we can dope silicon with N type, or we can also dope silicon P type. The thing is that silicon becomes useful, or we can make devices if you join this N type semiconductor and P type semiconductor together, and we join them together, then something happens, then a junction forms, and it is really action at this junction which allows us to make devices. So, what is interesting is not the semiconductor material by itself, but some modifications to it in different regions and realizing some regions. So, if we were to do this, then we still need equilibrium band diagrams. If we join two materials, then the question we ask is what will be the equilibrium band diagram, still sticking to energy versus position. That means I have joined two different materials. Question is how EC and EV, how should I draw EC, EV? Just in this case right here, I have drawn EC as a straight line, EV as a straight line. That was done saying that if I have this material, EC here and EV here, EC here, EC and EV here, or EC and EV here are at same position. So, if this is the position axis, then EC, I can draw EC as a one line and EV as another line in energy. And in energy I can draw as, I have drawn a gap, and that is what I am showing you down here as EC, a gap between EC and EV, and it is a straight line, straight horizontal line, because they do not change with position. Now the question is, if I join two materials, what will happen? How would I draw this EC and EV, etc. So, now this is what we are going to learn in this lecture. To further refine what I am talking about, let us look at what we are going to do in this lecture. What happens, the questions we will answer is, what happens when you join two semiconductors of same kind or materials? Example of this I have already spoken would be like silicon, except that one is N type silicon, other one is P type silicon, but nonetheless material is the same. Material is same, that is silicon. Only difference is that one of them has a N silicon has, for example, N type silicon has phosphorus doping in parts per million, very small amount. Similarly, P type silicon has boron doping, again parts per million, very small doping in it. Otherwise material remains the same, it is the same kind of material. Alternative is, and that becomes very important, which you will learn in optical properties, when you make heterostructures. Heterostructures are made, for example, in quantum dots, quantum wires, or LEDs or very high speed transistors, where we join dissimilar materials. We take two different semiconductors and join them, and in that case the question is, how does the alignment of the band happen? And in this cases we are going to learn about three cases. We are going to learn about three cases in heterostructures. One which will be called as straddled alignment, other one would be staggered alignment, and the third one would be broken alignment. What we mean to say is, for example, take this case. Let's use another pen. For example, we are talking about something where we have a large band gap. One material has a band gap which is EC and EV like this, but the other one has a smaller band gap. Now we have dissimilar material, there are two different materials. So the second material has a band gap which is much smaller, its EC is here and its EV is here. This is a smaller band gap material. For example, this may be, this could be gallium aluminum arsenide, whereas this may be gallium arsenide. This material may be gallium arsenide. So this was a smaller band gap, and this straddled alignment means that within the large band gap, the second material has its alignment somewhere in the middle, between its EC and EVs in the middle, as I have shown in this picture. In contrast, you could have this staggered alignment, in which case if one material's band gap is like this, EC, EV, then other one has a EC and EV which looks like this. In this case, notice this is EC and this is EV, maybe I write a little bigger here, EV. This is EC and EV of two materials. You can see here in this particular case, here EC is by EV is, this is the band gap of one material, this is the band gap of the second material, but the EC and EV alignment is such that the two materials are in their energies they are staggered. Example of this would be gallium, well, I give you another example little later. Third case is this one, where it is broken alignment, meaning thereby if one EC and EV are like this, then in that case the other one is completely off, something like this, EV and EC is like this, and this is for this case itself here. So let us make a line like this. So this is for this case, here EC and EV are off completely from EC and EV of the other material. So these are the three different cases in case of heterostructures. In case of heterostructures, these are the three different cases, and then the same kind materials, in which case it's only silicon or any one material, and in that case what is different between those two materials? It's really the doping which is different between the two materials. So these are the band diagrams we're going to study in this lecture. Now let's start with this silicon band diagram, or for example N type and P type silicon. It need not be silicon, the thing is that it should be same material. So let us look at this classic example, where we have P type silicon and N type silicon, and we are going to make a junction of it. Let us start first with a material which is, silicon. Let us take any silicon first of all. Let us define some quantities here. Let us use different color pen. Let us say this is EC of silicon, this is EV of silicon. Now we are going to choose a reference energy. In lecture number 16, you will recall we had chosen different kinds of reference energies. In lecture number 16, where I was talking about dopant levels and acceptor levels, I was saying that because energies always appear in difference, you will have some energy minus another energy, and hence what reference you choose cancels out, but nonetheless all energies must be measured to a common reference. And in that example, I was saying let us choose a reference arbitrarily, reference energy as somewhere here as 0. Then I said okay, let us move on and let us choose this point as 0 energy, let us choose EV as the reference energy, etc. In this lecture number 16 is what we had done. Today what we are going to do is something different. I am going to erase this, and today what we are going to do is we are going to choose a vacuum level as our energy, reference energy. So this is the vacuum level. So this is the vacuum level. Let us choose this as a reference, and we will measure all energies from here. What are the important energies with respect to this vacuum level? Now one energy is this energy, which is defined as electron affinity. Other energy, of course, you already know is the band gap. So that sets another energy level which is like this one. This is called ionization potential. Of course, typically what we do is we work with this electron affinity and band gap. These are the two quantities we work with. Ionization potential then is automatically known. Now why these names? You may just pay a little attention to it and try to understand why it is called electron affinity. Remember, let's assume temperature is 0 K. Remember, up to this valence band level, electrons in this band are completely full. Electrons are full up to this point, to the top of the valence band. If you want to make an EK diagram again, we can do so. We can do a EK diagram. Here is EV level. So this is the valence band. And here is our conduction band, energy versus K. So here is, this is the EV level and this is EC level. Remember, electrons are full up to here. Up to here, all the electrons are completely full. We have electrons all over here, completely full. This band is full with electrons, and the conduction band is completely, this conduction band is completely empty. So now, if from vacuum level, if you want to put an electron into semiconductor, where will you put? You are going to put into this level, EC level. So this energy, therefore, this energy from vacuum level to the conduction band, therefore represents affinity of this material to take electron. So that's why the name is called affinity, electron affinity. On the other hand, if you want to take out an electron from the semiconductor, then where will you take this electron out from? You are going to take this electron out from the top of the valence band. That's the one which will have the highest energy, so it will be the easiest to extract. So if you take this electron out and make it completely free, take it away from the material, that means you are going to have to take electron from the top of the valence band here and all the way to vacuum. So therefore that's how you will ionize the material, and hence this is called as ionization potential. This level is therefore represents ionization potential. What we will of course work with is electron affinity and the band gap. Those are the two sufficient quantities from which we can derive all the things. Now in this, one more quantity you may be interested in is that there would be a Fermi level also. There will be a Fermi level also. Let us say here is Fermi level. This is the Fermi energy somewhere here. It is a p-type semiconductor. Let us assume that this is a p-type semiconductor. Now, which ones are the material properties? So the question is, which are the material properties, meaning thereby once you say silicon, then they can't be changed, then that's what they are. On the other hand, there are some properties, some values, some of these values I am showing you, which you will be able to change. So which are those? let us mark them in, let us say, 2 different colors. Let us use this color kind of box for these quantities and this color box for this kind of quantities. So, let us use this and see. You see, electron affinity is a material property. Once silicon is specified, then its conduction band is specified, this edge is specified, and hence electron affinity is specified. The band gap of silicon is fixed, you can't change that. Once when you say silicon, then it has a band gap. Valence band edge is specified, ionization potential, therefore all these quantities are material properties. Once you say silicon, they are all set, already set. But this some other quantities you can change, and that's this quantity Fermi level. That we have learned in several of previous lectures, where we have derived carrier statistics. You know that you can put a donor phosphorus in silicon or boron, or acceptor in boron like acceptor in silicon, and you can move Fermi energy. And we start calling this as a p-type semiconductor just because it has been doped by boron, and therefore Fermi level has moved close to, this Fermi level has moved close to valence band. And you know that if you dope n-type, like with phosphorus, you put in silicon, in that case Fermi energy moves up and it goes closer to conduction band edge, and then it is called n-type silicon. But you see, EF you can manipulate, move it up and down in this band diagram based on what doping you do, that is under your control. So, this is the quantity which you can change. So, with these things in mind, let us move on and start drawing the band diagram. So, what I am going to do is, then let us take two materials, one is right here, this is the vacuum level, and this is the other material. Let us draw conduction band, valence band, conduction band, valence band of the other material. So, this is EC, this is EV, and let us call it 1, let us call it 1, material 1, this is EC2, conduction band of material 2, this is conduction band, valence band of material 2, and this is the vacuum level. This is the vacuum level. So, this is affinity of electron, call it 1, and this is affinity of electron, call it 2, and in this case is equal to the same electron affinity. And similarly, EC1, EG I should say, EG1 is equal to EG2, the band gap of the two materials is same, because the same material silicon we are talking about, and hence the band EC and EV levels align with each other, unlike the heterostructures where they were a straggled type or staggered type or broken type. So, here in this case these two are aligned well together. Only difference is, let us say one of these materials is p doped. So, here is the Fermi energy and here is the Fermi energy for this particular material. Alright. Now, since this is different, so we are going to give it a name. This material of course is n type. So, we got Fermi energy n on the n side. This is p type EFP. This is on the p type, Fermi energy on p type. So, that is what this material is, and we have not joined them. These two materials are lying, so n type material and p type material lying next to each other, but we have not so far joined them. So, question is, what will happen if you join them? We will first answer this mathematically and then examine physically. So, that is what we will do. First we will examine this question, what happens if you join them. Where I am taking you is, I am going to prove that these two energies must become the same, they must become equal. That is what I am trying to take you to, and we will see why what this happens. So, first we will answer this question mathematically, and then we will examine it physically as to why this should happen. So, let us do that. Let us consider this, that on this side I have p type material, on this side I have n type material, like in this page. On this side, on the left I have p type material, on the right I have n type material. So, I am continuing with this. So, what will happen? Electrons are going to go from this direction to this direction, and when you join them, electrons are going to try to flow from p to n type, and they will try to flow from n to p type. Thermal equilibrium is reached when these two rates of electron transfer from p to n and n to p are equal. So, let us look at this condition as to what will happen. So, if Ne is population density of filled states and V E is population density of empty states, meaning whole like, if this is the case, then what is n, what is this function? We have already learned this before, that this quantity will be equal to G of E, which is the density of states times Fermi function, the probability of finding electron at energy E. Recall, if you have already forgotten, then remember we had done this, we had calculated n as equal to, we had integrated from EC to infinity, and what had we integrated? We had integrated G function f e dE. This is what we had integrated to calculate n when you are calculating equilibrium carrier statistics. So, that is what we had done. So, what is, so really this quantity n of E is really equal, is this quantity. This quantity is n of E, what we are talking about. So, Ne dE therefore represents number of electrons per unit volume in and in this interval, in this energy interval. So, that is what this quantity n really represents. So, that is what this population density is. Similarly, V of E we will write as same density of states multiplied by probability of not finding an electron, which will be f of, since f of E is probability of finding electrons, so 1 minus f of E is probability of finding holes or not finding electrons. So, this is what these two quantities would be. Now, let us look at what would happen. So, what would this transfer depend on? What would this quantity depend on? Let us make it a red color. What would this depend on? Transfer of electron from p to n side. Clearly, this rate would depend on, this particular rate would depend on two factors. One is number of the filled states on the p side, and the second quantity it will depend on is number of, sorry, let me write this properly. So, this would depend on number of filled states, but which side? On the p side. So, I am going to use the subscript p to indicate the site, and since we are transferring from p side, and it will depend on number of vacant sites here, because electrons have to go from here over to here. So, whatever the number of electrons here are, they must, and there must be a vacancy here to take the electrons on this side. So, they will depend on n on the p side and v on the n side, the vacant state on this side. Whereas, as far as this transfer is concerned, it will be exactly reverse. It will depend on the filled states on n side filled states, it will depend on, so we are going to use n here, and it will depend on the vacant state on this side, because electrons have to go from here to here. So, it will be vacant of on the p side, this will be, and in thermal equilibrium these two quantities then must become equal. These two quantities must become equal, then only we will have equilibrium. So, let us see what will happen in this case. So, let us go to the, so I am going to write this here a little bit more nicely, n of energy V on p side should become equal to n of p when in thermal equilibrium. So, let us do that again next page. Let us write this out, maybe I write it one more time. So, just for continuation sake. I just copied the same line, and let us write down what this n is. Remember, n is g on the p side, g on the p side times f on the p side. What is V? V is equal to g density of states on n side times 1 minus Fermi function on n side, and this should be equal to likewise g on n side f on n side g on p side times 1 minus f on p side. If that is the case, now you can see I can cancel this out with this and this. So, I have f of p this implies clearly f on p side, Fermi function on p side should be equal to Fermi function on the n side. From this you can derive this. What does that mean? And we know how we can write this. Fermi direct function is written as 1 plus exp. You can write this as E minus EFP by kBT should be equal to 1 by exp f on the n side by kBT. Remember what these quantities are. Remember these quantities are Fermi levels on the p side and on the n side, and for this you will have to go back here. Remember, this is the quantity I am talking about, Fermi function, Fermi level on the p side, Fermi level on the n side, and that is the question we were trying to answer, whether what will happen when you join them. And I started saying that I will prove to you that these two must become equal when you join them, and that is what we are heading towards. Now you can see from this relationship which you see, this implies that E F P energy Fp on the p side should become, Fermi energy on the f p side should become equal to n side. So this we have been able to prove that these two Fermi energies should become the same, and that you should be able to see from here itself. This Fermi energy at 0k represents chemical potential of electrons, and even at slightly higher temperatures, the kind of temperatures we are dealing with, even at that point this Fermi energy still represents very closely what the chemical potential of electrons are. So, if you have these two materials and we are trying to join them, clearly the energy of electrons on average on this side, on the n side of material, is much larger than on this side. So, clearly that electrons would like to move from this side to this side, and when they do so, what will happen? This level, Fermi level, will start going up a little bit. Remember, whenever you add electrons to the system, that means you add, for example, donors or electrons, then this Fermi energy starts moving up, and you take out electrons and add holes, then this Fermi energy starts moving down. So, you are going to add electrons from here to here, and anyway this side has lot more electrons and this side has lot more holes. So, holes will like to flow from here to here and electrons will like to flow from here to here. So, consequence will be that this Fermi level will start going up a little bit, and since electrons are moving out of here, so this Fermi level will start moving it down until the two Fermi levels become equal, and then the chemical potential is the same, and this process will stop and you would reach thermal equilibrium. So, this is the basis on which we make these band diagrams. So, since we require this, then let us see how we can make the band diagram. So, let us again do this. So, what are we going to do? Let us draw those band diagrams from number 6 again, that we had said that here is the vacuum level, here is the vacuum level, and here is EC and EV of one material, EC, EV of other material, and they are same since they are silicon, only one has a Fermi level here, other has a Fermi level here, and we have not joined them. We intend to join them right here. We intend to join them right here. This is where, let us call it x equal to 0, or let us call it metallurgical junction. This is where we want to form a metallurgical junction. So, we are going to join them. So, let us do that, let us join them, and this is the vacuum level, of course. So, if we join them, then let us take the steps. What we want to do is, first thing is that the Fermi level must be same, that is what we have learnt. If this is where this metallurgical junction lies, this is x equal to 0, this metallurgical junction, then we know that Fermi energy should, this is EF on the n side and this was EF on the p side. Now, when we join them, there should be a common Fermi energy. Fermi energy cannot be different. If there is a gradient in Fermi energies, carriers will flow from one wherever the energy is higher to the other side until they come in equilibrium. Okay. So, now what we are going to do is let us join them. So, once Fermi energy becomes equal, so I would imagine as if the way I will draw it is that I will say, okay, n type semiconductor, I will look at this semiconductor and say I will draw this semiconductor just as is. And I look at this semiconductor, this particular semiconductor, and I join them also. This was p type semiconductor, so I will keep its p type corrector like this. And when I have to draw the vacuum level, what I will do is I will draw the vacuum level with the same gap, whatever the gap here was, I will draw this same electron affinity, whatever this electron affinity was, and what I am going to do is draw vacuum level here, and this is electron affinity. Now, notice what has happened. So, this is EC, this is EV continuing. So, the EC and EV if I draw, I should draw, now when I have joined them, I should draw it like this. And when I say vacuum level, then vacuum level must be going something like this, then must be following like this. So, that everywhere, the problem is right here, problem is right here. What is the electron affinity? What is the potential? Notice the potential, here is the vacuum level, there is a potential here, and this potential, there is a discontinuity. Now, potential, why should this potential have discontinuity? In fact, we require continuity of potential here in this particular case. It is possible to have discontinuity potential also if there were some dipoles present here. If there were some dipoles at this interface, then it is possible, but we are neglecting that. We are not, we are assuming it is the same material, homogeneous material, both are silicon pieces. So, and this n type and p type doping alone cannot produce dipoles. So, we expect this vacuum to be this vacuum level to be continuous. If that is the case, then I would be able to draw this vacuum level as a continuous level if I, instead of doing it like this, let me erase this and clean this up a little bit. If instead of drawing it like this, if I had drawn a little bit smoother, namely something like this, something a gradient in between, and similarly a grading in here, a grading in here. Let us see what will happen here. Let us try to do this one more time. What we are going to do is, now we will be able to draw a band diagram a lot more easily with this understanding that we say, I will redraw this diagram. I will say this, here is a metallurgical junction, x equal to 0. This time what I am going to do is again draw the Fermi level. Here is the Fermi level, EF, and what I am going to do is now I am going to draw this semiconductor p type, but I will not go all the way to junction, I will stay away from it little bit, for a little bit. I will draw this n type junction, and I will draw these vacuum levels, and this vacuum level a little higher, and stop here. Then I will say that look, what I needed was that vacuum level should have been continuous. I will therefore very smoothly join them. Instead of abruptly, I will join them smoothly. If I do that, then in that case, well, how fast, how slow, what is the value here, that you will learn quantitatively also. I am just qualitatively showing you that this should be smoothly joined so that it is continuous. So that is why I have shown you qualitatively. Later in some other lectures, in future lectures, you will quantitatively derive also this portion of the curve also. And now similarly, because every place it should be electron affinity, it is a material property, so we can with same values, same slopes, I should be able to join these. So that everywhere this remains electron affinity, and this remains the vacuum level. And now I have got my band diagram, EC, and here is EV, and the Fermi energy is common. What has happened is, semiconductor, something happened to the semiconductor here between these regions. This is minus xp, let's call it xn. In this region, that when we joined two semiconductors, they were affected and the band diagram changed, whereas far away from this junction, semiconductor remained as it was before, and hence and the only place where the change was in the interface, and how the change was along like this. And this is the easiest way to visualize this band diagram. So this is your E versus R diagram. This is E, and this axis is position R, and this becomes a combined band diagram of two materials together. Okay, so one point you have to remember, that if I take, say, this as a 0 reference of energy, then I have changed this end of semiconductor by amount, this much amount. This typically is called as QV. Let me remove this vacuum level right here. So this is right here. This is the vacuum level, and I am talking about this energy is written often as Q times V Bi, the built-in voltage. Remember, voltage multiplied by Q is energy. So that is a QVBI. And notice that this end will be at higher, this end of the semiconductor would be at higher potential, not energy. Q times potential is energy. This we will learn a little bit later in further detail, but Q times charge times potential. So this end would be at higher potential. Remember, electron energy increases in this direction. So hole energy increases in this direction, which means potential also increases in this direction. So this is the electron energy, this is the hole energy increasing in this direction, and therefore potential also increasing in this direction. So since this end is at lower, therefore, so this end would be at higher potential, and this would be at a lower potential. What that will do is, and the same built-in field I have shown here also, but after all it is the same thing, same quantity. This is Q times VBI, and remember this quantity is also Q times VBI. Remember this quantity is also Q times VBI, and remember this quantity is also, between this diagram, this quantity is also Q times VBI. Remember, it has happened because we have tried to move the two Fermi levels together. So the amount of shifting that we have done is the difference of EFN and EFP, and that's the, by that much amount all the levels have moved, and hence that's the built-in voltage. That's the voltage which has been built in. Now if this end is at higher voltage than at this end, then the electric field will set up, and this electric field direction would be like this. This is the electric field direction. Why? With this higher voltage on this side, there is a lower voltage on this side, so electric field that is set up in this direction, and that you can see, because when electrons go from here to here, then what happens? They leave behind P plus charge here, phosphorus atom, and it remains ionized. This is a donor atom which is ionized, and the fifth electron is gone. It has gone on this side. And what happened? This electron which went on this side, there are a lot of holes here. This electron and hole recombined and annihilated each other. So what happened? That led to, on this side, some boron minus were left. That means acceptor ionized. Remember, boron minus and a hole are neutral. The electron which came from the other side annihilated the hole, so what was left was B minus, boron minus. So now I have charge, negative charges lying here and positive charges lying here, then clearly electric field will set up in this direction. That is what we are seeing also in this case right here. So that is how, but this is the part, since you will be learning about p-n junction lot more, I thought that I tell you about the band diagram right now, and later when the device is done, p-n junction, this whole story will be repeated. At that point of time, this band diagram will be immediately drawn, but we will do quantitatively at that point of time and derive all these, whatever the curvatures you see here, whatever this, by how much amount they will fall apart, fall down, how much, what will the built-in voltage, etc. will be carefully calculated. And that time you will have another opportunity to learn. But let's now move on to heterostructure, which we may not cover in much more in that much detail later. So now, so this is something where making band diagram gets a little bit more tricky. But I think now that you have learned some concepts, it will be fairly easy. So we are now going to talk about this heterojunctions, and as a first case, let's take this straddle type. Let's take this straddle type alignment. Remember what was straddle type alignment? In that case, the way we have shown this picture here, right here, as we are showing, this is the vacuum level for one material, and in this material we have, which has the electron affinity psi 1. That's why it's showing here. Its conduction band level is EC1, its valence band level is EV1, and band gap is EG1. It is a larger band gap, and the other band gap is straddled. EG2 band gap is a small band gap, and it is straddled between these two. So when it is straddled here, EC2 that means is here, and EV2 is here. That means EV2 level is higher than EV1 level, whereas EC2 level is lower than EC1 level, and hence the word straddled is being used, which also means that the electron affinity will be higher. Now, what do we do here in this case? How do we make band diagrams? In this case also, remember the Fermi energy, which I have not drawn yet here, I have not drawn that Fermi energy, but that Fermi energy will have to become equal. That we are going to put there in a minute, but just wait for a second. But the question is, what would be the, when we join them, remember EC1 minus EC2, that's the band offset in the conduction band at this point in time, when vacuum levels are aligned. When vacuum levels are aligned, when vacuum levels are right here, at that time there is a conduction band, and EC1 minus EC2 is some number delta EC2, that delta EC. Question is, when you join them together, then what will be that EC? That is the question we want to ask. So what do we do here? So how do we answer this question? And that is a trick, how you need to know that in order to be able to make band diagram. So according to this Anderson, so what we are going to use is what is called as Anderson rule or electron affinity rule, which works well in most cases, and the end I will point out when it may break down. And then based on these we will be able to figure out band offset. What do these rules say? They say that the band offset will be delta EC, that is after they join them, then this band offset will be equal to psi 2 minus psi 1. That means when you join them, if you look at right now, what is the band offset? That is, what is value of EC1 minus EC2, clearly that is psi 2 minus psi 1 when they are not joined yet. And what point being made is that after you join them, it remains the same. And by the same token, you should be able to see this, that if so, this value is delta EC, and this value is delta EV, and delta EC you can clearly see is psi 2 minus psi 1, which is written right here, and that after joining also it remains the same. And what is this value now? This value now is equal to delta EV is equal to EG1 minus EG2 minus delta EC. You subtract this and subtract this quantity, and you will get this, which you subtract out of EG1, subtract this amount and subtract this amount, and you will get this. So, that is what this quantity is, and the point is after joining also it remains the same. That is what this Anderson rule or electron affinity rule says. Once we know that, let us see how this band diagram is to be drawn. And now it is fairly easy to draw this band diagram. So, let us do that. I will have to make it one more time. Vacuum levels we have to be very careful about. So, we are going to do that, and then we are going to make a straggled EC and EV. Maybe I make this a little bigger so that picture remains a little cleaner. And in this case, let us choose now Fermi energy also. Let us say this material has a Fermi energy of this much, it is N type material. Let us say this one is P type material. This is a P type material. So, we are going to label this now. This is EF on second side, and this is EV on the second side. This is EC on the second side. This is the vacuum level. This is electron affinity on the second side. This is the vacuum level. This is electron affinity on the first side. This is EC1. This is EF1. This is EV1. These are the quantities. Now, we again know that if you want to draw the band diagram, it is very easy. What we have to do is first make common Fermi energy. If you join them, we are going to join them right here. Right here, we are going to join them. You are going to join them. So, first thing to do is make common Fermi energy. Fermi energy must be common. So, if you make Fermi energy common, then what happens? That is what we need to look at. Let us draw it far away. Again, look far away from interface. Far away from interface, we are assuming the semiconductors are very long in this one in this direction and this one in this direction. So, far away interface, they will be unaffected. If that is the case, then with respect to the Fermi energy, EC level will remain the same. That means N type behavior will remain the same. So, we are going to draw that. So, right here, I am drawing the same band diagram as which is on up here. I am drawing this, and same thing will happen here also. The far away, it will remain unaffected with respect to this band diagram. EV level P type behavior will maintain its P type behavior in the same way, and here would be the other level EC2 level, whatever this distance was, approximately same distance. We are going to draw this. Now, if you want to draw the vacuum level, then we have to do draw the vacuum level. That is the most important part to draw. So, I am going to distance about this much distance, psi 1, I am going to draw this vacuum level. So, here is the vacuum level I have drawn, and from here psi 2, remember psi 2 is bigger than psi 1. What we have done is, we have imagined that we have lifted this part of the curve higher up to this Fermi energy has been lifted up to here. So, by this level amount, this level is also lifted, by this amount this level is also lifted, by the same amount this level is also lifted. So, whatever the difference here was, since I am lifting this Fermi energy and aligning it. So, we have to lift this vacuum level also higher by same amount, whatever the difference in Fermi energy was. So, let us say that vacuum level goes here, right here. This is the vacuum level for this one and this one. This is the vacuum level here, right here, and this is the vacuum level here, and I have not drawn, So, this is the, now let us label them. So, this is EV and EC, and remember this is EC and EV, and remember now I am not writing EC1 and EC2 because now it will be continuous. So, I have joined them. So, there will be one valence band level and one conduction band level. It may change from place to place, but I have to join them together. So, therefore, now what I am going to do is, again we are going to smoothly join this vacuum level. because we can't have discontinuity. That is why we can't have discontinuity in vacuum level unless there are dipoles. Assuming there are no dipoles, then this is okay. So, if that is the case, then I am going to draw in a way where this material, since this is a material property, psi 1 is a material property, everywhere, every point in this material, this particular material, this must remain psi 1. In fact, let me give you an example, and then only it will make, then you will appreciate it maybe a little bit better. Let me give you some material names also. Let us assume that this is, let us take this material as, let us write down here, this is gallium, aluminum, arsenide, and this material is gallium arsenide. Let us say this is gallium, so this is gallium arsenide. All right, these are the two materials here. This is aluminum arsenide. So, this is this material which whose psi 1 is known. So, as long as on left of this line is always, it must remain psi 1. So, it must also lift same way, this must be psi 1. What happens on this side? On this side also this curve must go the same way as it has here. On this side the vacuum level is coming down, and this distance must always be psi 2. That means this region would be going like this. So, that this is psi 2. This is psi 2. So, that is psi 2 electron affinity, and in this case what do you see? What is this quantity? Let me write it far away. This is delta E c. This is delta E c, which is equal to psi 2 minus psi 1. And now, similarly, I am going to draw this part of the band diagram. This must also therefore exactly follow that, because this everywhere it should be Eg, Eg1 in fact. It should be Eg1 everywhere, and this must follow exactly like this, because everywhere it should be Eg2. And what is this quantity? This is clearly delta Ev. That is the delta Ev. Now, if you look at it, then if I draw only the black lines, then this band diagram therefore looks something like this. I am just copying this for your convenience with a clarity, little bit clarity. It looks something like this. So, this is Ec, this is Ev, and this is Ef, and this is what you get your band diagram as. This is very important. Now, you will see in making high mobility transistors, you can lock in electrons in this region, and these are the things which help in making controlling device characteristics. These junctions are very important, and which is why I have made some for you. For example, also in LEDs, you will see you will have to take semiconductor which is like this, you will take another semiconductor which is in the middle, and then you will take another semiconductor which has a bigger band gap. 3 semiconductors you want to take something like this, and you are going to make LEDs with this will be Ec and this is Ev before joining. When you join, this nature will change, as you have seen. This is what I was trying to teach you, how this junction area will change in their behavior, like here. When you join them like this, then they change to this behavior. Same thing will happen here, and this is, you will see, you will use this in LED, and hence these type of diagrams are very important. And I have given you example of a straddle type diagram, and now maybe we could try another diagram of same kind, wherein let me quickly do it for you on the screen. One more type of diagram. For example, if you were to take a material, and in fact I just give it to you 2 diagrams, and you try it out and find out whether it is true or not by trying it out. Suppose it's one material is like this, other material, it's the same material we are talking about, which we have drawn in the previous page. I am still continuing to use this as an example. Let us say we are using the same example, except I am going to change the Fermi level as to where this green lines are. Whatever these green lines are, I am going to change the location and draw everything in, then ask the question, what happens here? In this case, let us say we make this one p doped and this one n doped. Then what happens? In this case, the band diagram you are going to get is a common energy far away, something like this, and we are going to join them here, right here, and this is the conduction band. Now, if I take this material, then it is far away, it remains as is. And now, if we join this, what is going to happen in this case? I am just going to draw it for you, and you should be able to practice it. Whereas, in this case, you are going to see something like this, and you are going to see something like this. Oh, sorry, this is wrong. Because this should be Eg2 all the time. And this time, whatever happened in the previous diagram, you got this feature in the conduction band, and this type of feature, which was this was delta EV, of course. Well, we have drawn it right here. Anyways, so in this case, it reverses. This kind of feature goes in the bottom. You should be able to try this exactly using the same level, and the vacuum level, of course, will in this case would remain something like this. Vacuum level will look something like this. This will be the vacuum level, and this will be the EC, and this will be the EV. This will be EV. So you should be able to practice this diagram. Let me try one more, and that's will end. If you look at this another material, like say type 2, the second one we were looking at was this was a staggered type. This staggered type is fairly easy also to draw in the same way. Maybe this will be given in. I will give you this as this example, this one in as an assignment maybe. So in this case, this is a staggered type of diagram where you have a something like this. For example, in gallium 0.6, aluminum 0.4, antimony. This is a compound semiconductor, and another semiconductor which is indium gas. This is indium arsenide. Indium arsenide is this material, and this is the staggered type. And I will ask you to try to draw the band diagrams in such cases. What I will do is one more attempt toward the third one, which is the broken type, and this will be like my last example. Broken alignment. Let's look at this one. This diagram as to what will happen in this particular case. So let's look at it as follows. So let's look at in this case, we can take a vacuum level. Maybe we can put a break in here, and in this case, since it is a broken type, so let's say we take this as this is one semiconductor, and the other semiconductor is actually even below this. So this is EC2, this is EV2, and this is EV1, and this is EC1. And what we are going to do is we are going to join them here, somewhere here, we are going to join them. Unfortunately, in this case, the EC2 level is even below EV1 level, and hence it is being called as broken alignment. Let us assume, just so that this Fermi energy to be here p type, this is EF1, and let us take this n type, this is EF2, and deliberately I am doing that, otherwise the alignment will be too much off the screen, and hence it will be difficult. And this is psi 1, and this is psi 2. This is electron affinity of the second material. What happens if you join them again? Remember, the way to do it is, imagine material on the right, you lift it up so that the Fermi energy becomes equal. So that is what you do. Draw the Fermi energy, draw the junction. What you do is always one material, on the left material, let us draw it completely. So here it is, and we will just stay away from the interface. Far away we have drawn, material does not change, it remains as is, and I am drawing the vacuum level also right here. Here is the vacuum level, this was psi 1. This was psi 1. I am drawing the same diagram as it was before. Now, what we done is, on the right hand side, we have lifted it up so that the Fermi energy becomes equal. So, the amount by which I will have to lift up is this much. So, let us do that. So, vacuum level will get lifted up by that much amount, and when we do that, then your conduction EC2 level would have come here, and this level would have in this case come somewhere here. This is the second one, and now what happens? Again same thing, smoothly join these. Join this vacuum level. This is my vacuum level. Smoothly join it, and now use these xi's for the material. They must remain the same. Now it's easy. So this material should go exactly same way. Right here, it should go up. So this material should also go up. Same following, so that this band gap remains same. Eg1 remains Eg1, and what happens to this material? This material, for this material, this must go something like this and something like this. This should bend something like this, because remember it should follow, this must remain psi 2, and this everywhere should remain Eg2, and therefore this black is EC and EV, this is EV and EC. We get a diagram which is this is EC. We get a diagram which is of this kind. So, this is the thermal equilibrium diagrams. This is thermal, it is in thermal equilibrium band diagrams in thermal equilibrium. This is where I am going to end my lecture. That I have taught you how to make band diagrams, how do you make junctions, how do you join two materials together and draw the band diagrams, because I told you in semiconductors it is really junctions which are important to make electronic devices. If you did not have junctions, electronic devices will not be there. But when you do that, when you make devices, you must know how to make these band diagrams at junction points. If you learn, because this is the thermal equilibrium. After that you perturb it, after you apply after that you apply voltages or current, and the device starts behaving. But in order to understand how it behaves when you apply some current or voltage, how device would work, you first have to understand what the thermal equilibrium picture is. And that thermal equilibrium picture I have shown you in different cases, how these diagrams can be drawn. And maybe I will write finally, the absolutely final, let me give you this example of this material also which we are talking about here, like this could be gallium antimony, and this material could be indium arsenide. This is the broken time band diagram which I was trying to show you. So, with this let me end the lecture. Thank you.